But one main component that is in just about every power supply that I've ever worked on, there are a few, is they don't have the transformer. And of course, the transformer is the device that gives us the voltage required for our output. So we all start here when we're looking at trying to design is what's required by the load, or loads that I'm planning on running. So, you have multiple loads on your automobile. Then we're going to go through a regulator. A regulator is going to give us a almost constant output, even with varying loads, and also varying input voltage. So this is going to give us an almost constant DC. Out of our rectifier, we either have, this is a half-wave rectifier, of course, because it's only got one half of the alternation. One half of the cycle. So that's a half-wave rectifier. Today we're going to start looking at full-wave rectifiers, but this is half-wave. But once we add the filter, we'll never see that, but we'll come up here. So this would be basically what we get here. Then we're going to filter it, and then we're going to get this stuff out here, which we'll talk about where that comes from. This is going to be unregulated, which means that this ripple, we call it a ripple voltage on the top, will vary with loads. And if it varies with loads, then that means the DC out of the filter is going to vary with loads and also input voltage. So what we're looking for on a DC power supply is this voltage right here is not guaranteed. In fact,
Mr. Raymond, are you trying to share your screen?
No, yes I am.
Oh, we can't see anything on this side.
Oh, okay, because I didn't share my screen. So
you're not recording either. If you want to be recording.
Yeah, I am recording. See the little pause marks over here. You don't see me share my screen, but yeah, I'm recording. So since I'm not sharing my screen, you can't tell. I'm not using the Collaborate record anymore because it's not good, because for one thing I can't pause it. I can come down here. Another one, what I had to do was to keep from wiping out the previous recording, I'd have to stop the recording, log off Blackboard, come back in, and start everything back up. With this software, and these will not be on Blackboard, by the way. These will be up on YouTube in my Blackboard site. My YouTube channel. So like I told y'all can go up and search for Rich Raymond, and then in the search window on YouTube, not on the search tab for your web browser, but on the search for YouTube. And then I should pop up. I'm about the second one, and it's got a picture of me. So thank you, Lee. I'm sorry. And like I said, there's so much stuff to remember. So this is the basic makeup of a power supply. Actually, there's one more unit on here, which we usually always have, and this will be before the rectifier, and this is going to be a transformer. So very seldom do we rectify the input voltage on a linear power supply. And a transformer is actually going to come over here, and this is very, very important to choose the right one. So not only is it going to have to supply the required voltage for the load, it's also going to have to provide the current, the required current for the load. And that's what we'll look at. So that's the main thing. First of all, this is what we're talking about. This is what the power supply is designed around. It's designed around the load or loads that you want your power supply to run. That's the first thing you're looking at. How many loads you're going to have to run. And then, of course, we're going to look at, we're starting off with unregulated DC power supply, or we're starting off with unregulated, unfiltered. which are still very popular because they're the cheapest ones out there. And then we're going to move into unregulated filtered. And then we'll move into regulated power supplies, which means the output will stay almost constant even though my input voltage varies. And that's the problem we have, is this input voltage right here is not fixed coming into my transformer. So National Electrical Code calls it the nominal voltage, and it's 120 volts AC. But it's plus or minus 10%. So technically, it could be 12 volts up or 12 volts down, and it would still be considered legal. So that means I could have 90 volts coming in at your house, and your appliances and everything should be able to run on that because that's within the limits. So this 120 volts is just a nominal voltage that we set. Normally it's pretty close to that. I think if we measured this voltage here, like the other day, we had 117 volts, I think. So it's pretty close. And then, of course, it's got to handle slight variations here. And not only that, in load. So when you set up and you design your power supply, you got to take that consideration. So you got to give it plenty of leeway so you can actually maintain this. And we'll look at that. But the one thing that they're actually messing over here, of course, on 90% of the linear power supplies, the first thing we're going to have is a transformer. And most of the time it's a step-down transformer. Of course, we know the advantage of a lower voltage is that we can deliver the power more safely. But the current has to go up to deliver that power, right? So we figured out this. Of course, this is the one. This is the one I like to use. So full wave we'll use 2V peak over pi, and then for half wave we're using V peak over pi because half the alternation is gone. And of course, this is a half wave rectifier. And we looked at that. We looked at it on the oscilloscope. We came up with why we come up with V peak over pi when we have a half wave rectifier. And of course, like I said, you could try to remember these fractions, but I just like to remember the rule because the fractions vary. V peak out. So this right here we'll calculate as V peak, and this over here we'll call this V peak out. And this is going to be equal to V peak minus the VF, or the forward voltage drop of the diode. And all our power, we can ignore this when it gets up to a higher voltage, but when we play around with the low voltage like we're doing in our class, we're going to take out approximately 7/10, or we're going to take out 7/10. We're using what we call second approximation. So we're going to take out 7/10 for silicon and 3/10. And y'all can see just by our calculations, this has been really accurate. Let's see. So we got past here. We looked at this guy, PIV, which the most data sheets calls the peak reverse maximum. So PIV is what they teach in books. But if you're looking for PIV in a data sheet, odds are you're not going to find that. And we solved for this. Let's see. We looked at negative, and of course on half waves, what we're looking at is what side of the diode is pointing back toward the source. And we know the bar end is called the cathode, and we know the arrowhead is called the anode. So negative power supplies, let's see, full wave rectifiers. So this is where we start. This is where we left off at on full wave rectifiers. So what we're literally doing is using diodes. If we're doing a positive supply, what we're doing is we're taking, instead of clipping off the other alternation, we're going to take it and steer it up to the top. So what we end up with on the output, the other one's on the input, but what we end on the output is we end up with this. So back over here, if your input frequency is 60 hertz, and a cycle is how long it takes to repeat, then this right here would be a cycle. So the input, the other side would be doing like this. So the time between here and here would still be 16.66 milliseconds. And if we took the reciprocal of that, it would come up to be 60 hertz. So this is still 60 hertz. But when we get over here, for every cycle on our input, we get 2 cycles. So this is a repetition on an output. So on a full wave, your output pulse frequency is going to be my frequency N times 2. And that becomes a big feature when we start trying to filter this, and we'll look at that when we get into filters and try to turn this into a DC instead of pulsating DC. So here, instead of using, for DC half wave is going to be equal to V peak over pi, because we have to average in 0. Volts DC, I should have put volts DC. Full wave is going to be equal to, you can write this different way, 2 times V peak over pi, or 2 V peak over pi, or V peak over pi times 2, whichever way you enter it in your calculator, you'll come up and get the same answer. So automatically on a full wave we get twice as much out, DC out, than we do when we do a half wave rectifiers. But it's still pulsating, which means now it's going to pulse to ground. If it's 60 hertz, it's going, the pulse is, the output frequency is going to be 120 hertz. So it's going to pulse to ground 120 times a second. Everybody okay? So a center tap transformer, this is the first one we looked at. We have a 12.6 volt center tap transformer, and like I say, the actual trainer doesn't label this like it is. So 12.6 volts center tap, which means we would get 12.6 volts all across here, and we get 6.3 volts between here and here, and this is RMS. So on AC, if we don't specify RMS, then it's assumed to be RMS. So a transformer changes the level of AC voltage, changes the level of AC current, does not change the power for an ideal transformer. We have 2 sides. We have the primary, which always points back toward the source, and then we have the secondary, which points toward the load. Step-down transformer reduces the AC voltage to the load, and a step-up transistor, a step-down transformer reduces the AC voltage to the load, and a step increases the voltage. But if we step down, current's going to go up to produce the same amount of power. If we step up, current's going to go down to produce the same amount of power. So here's center tap. And of course, we have a 12.6 volt center tap. So it means if I was to give this thing exactly 120 volts AC, and we were operating at its rate, at the transformer at its rated load, then I would measure, if I measured from here to here, I would measure 12.6 volts. But notice our load is not connected between here and here. Our load is connected its common is the center tap. So that means all this guy up here is seeing relative to common. If I was to measure this is going to measure 6.3 volts AC. And if I measure with an oscilloscope from here to here, it's going to measure, or with a meter, it's going to measure 6 volts DC. It won't with an oscilloscope, because it'll actually show you 6.3 divided by 0.707. So all our diode sees at all our load sees at any one time is something that's going on with this guy right here, 6.3 volts AC. And this is one of the biggest mistakes that students make, is they see a 12.6 volt center tap transformer and they want to use 12.6 volts to calculate the voltage. And of course, they'll be twice of what they're supposed to have. So we looked at this relative to this. If we came over here and we put AC on here, and this is relative to ground. This is relative to common, by the way, and this would be hard to see. But if we came over here and looked at polarities, so just during the positive alternation, what this side would be, this would be plus, this would be minus. This would be minus relative to this guy, and this would be plus relative to this guy. So that's going to be a plus here. This is going to put a minus here. So and this is going to be a minus here, and then this is going to be a plus here relative to this guy. Let's do it this way. So as soon as I see this minus, that I know this guy right here is going to be turned off. This guy right here is going to be turned on. So this is going to let current flow out. Let me change colors. This is going to let current flow out of here through our common or our ground, back up through here. The bottom of the resistor will be negative, comes up here. It's not going to go this way because this guy here is turned off, and when a diode is turned off, it acts like an open switch. And it's going to flow up and going to go here and back to the positive of the transformer. So this is going to give us, it's going to let the positive alternation go through, minus about 7/10 of a volt, because the diode. So on the next alternation, this guy here is going to go negative. Down here is going to be positive. This is going to be positive in respect to that negative. This is going to be negative in respect to that positive. So what that's going to do is going to come over and put a positive on this guy. It's going to put a negative on the anode of this one. This guy right here is going to turn off. This guy here is going to turn on. So what's going to happen now, it's going to leave this. So flow out through the ground or the common again, flow up, goes through this in the same direction, which makes this side negative, this side positive, but it's instead of going up this way, your current flow is going to be down through this guy, back out, and up to the positive of the transformer. So what we do is we get another pulse. And then the next alternation, everything swaps. And it just keeps swapping and swapping and swapping and swapping. Now our output voltage, first of all, we'd figure out V peak here, or V peak secondary, I think it's what we actually call it, would be equal to it's going to be equal to 6.3 6.3 divided by 0.707. So what does that give us? Calculators. So first thing you ought to do in this class is get your calculator out, right? Because it's kind of like DC. So 8.9?
8.9.
Okay, 8.9. Good, guys. And this is peak. Then we'll calculate V peak out, which is going to be 8.9, and we'll assume these are silicon. So if I don't tell you germanium, just go ahead and assume it's silicon. And we're going to take out the VF. So V peak out would be equal to 8.2 volts peak. And then my DC, my volts DC, would be equal to 2V peak over pi. So they're what, 16.4 divided by 3.14. And this will be our DC. This will be what our meter would measure. So what we got? What's that? About 5.4 volts DC. And this is the one we looked up. I think we got 5 point something. I think we got about 5.07, but was only off, just a millivolts from what we calculated. So this is full wave center tap. So that would be the name of this circuit. Unregulated, excuse me. It's actually unregulated, unfiltered. Very popular. Charging, most battery chargers put this out right here. So if you ever took an oscilloscope and put it across your battery charger, it's full wave. Now what type of transformer it uses, whether it uses center tap or the other one, probably uses center tap. I think I've tore one apart. In fact, I've had one go out, and I've actually replaced one of the diodes actually burned out, and I took it apart, replaced the diode in there, it worked fine. So I don't know if I still got that one or not, but yeah, battery chargers will do that. If you don't have it connected to the battery. Now a nice big battery is a really good filter, but and what's nice about this, the diodes are only conducting half the time. So that means if I came over here and had a 1 amp power supply, this would have 1 amp here, right? And then it'd have 0 out there, so it would average out the current. So what this guy right here, its average current would only be about 500 milliamps. So this is another big advantage of this, is that your diodes can be have half of the current rating than you actually get out of the thing, because they're only conducting 1/2 of the time. So that's another advantage of a full wave center tap. The biggest disadvantage is the cost of this guy right here, center tap transformers, because they got to go in and put that tap at exactly the center and somehow bring it out of the transformer. So center tap transformers are more expensive than untapped transformers. And our transformer and our trainer. So when we get toward the end, what we'll do is we're going to open up one of these trainers and actually look at the power supplies. Look at the power supplies in them and see all these different components, figure out what they are and where they're at. And it's, like I said, it's variable, very repairable. We talked about turns ratio. A lot of the things talks about turns ratio, and they'll come over here. And normally, this right here, I've never seen anything where the secondary is a 1. So we might have one side is always going to be a 1. So if it's got a 2-to-1 ratio, what that means is, and basically the way we calculate this guy is out over in. So out, and we come up here and do this, so it's got, for every 1 turn over here, it's got 2 turns over there. So this is, if the ratio, if the 1 is on the secondary side, it means it's a step down transformer. And to figure out your ratios, you would say VN. Oh, I didn't screw my display in, sorry. Let me screw it down so it don't come out. So V out of the transformer, and these are AC, by the way. I'm going to call it T for transformer out, would be equal to Vn over the ratio, out over in, so times 1/2. That's how easy it is. And of course, if it was the other way, if it was 2-to-1, it's going to be out over in, but that's 2 over 1. So V of the out transformer would be equal to Vn times 1 over 2, which would be times 2. So that's all you have to do. I mean, just to calculate what your output. So if your turns on your secondary is, if you have more turns on your secondary than your primary, then it's going to step the voltage up. If you have more turns on your primary than your secondary, it's going to step your voltage down. Pretty simple. But it's out over in. It's out over in. And one side's always going to be 1. So on a step down transformer, it's going to be 1 over the turns in the primary. Now, normally they don't give you the turns ratio on transformers. What they usually give you is the output voltage and the input voltage. And if they give you the output voltage over the input voltage, then that's the way you would calculate the ratio, is just what? You can take V out over V in, and then that would give you the ratio. If it comes up and gives you a fraction, you know it's a step down transformer. And that would give you the number you're supposed to multiply by anyway, right? So this is one way we can do this. So like I said, most transformers, I don't think I've ever seen a transformer that gives you the turns ratio. What it gives you is it gives you the output voltage for an input voltage. And you could calculate the ratio if you needed to. But so there are several of these on the quiz as far as calculating this. Instead of giving you the actual output voltage, we come over here and give you an input voltage, like 120 volts, and then you solve it by the turns ratio. So everybody okay on that? Yeah. So it's out over in. Gains out over in, out over in. So we'll even look at that when we get into like amplifier circuits. It's out over in. If we calculate the gain, it's out over in. And we're going to introduce y'all to also what we call decibels, or dB. Which y'all probably heard of before, but we'll explain those for you too while we go through this. Each diode in a full wave rectifier is alternately forward and reverse biased. The amount of reverse bias that each of these diodes. Now the problem we have is when this guy right here is positive, when this guy here is negative, this guy here is positive. And instead of getting V peak over there, what we're doing is this guy over here is seeing this guy. This guy over here is seeing this guy. So what that means is your peak inverse voltage has to be your peak to peak voltage over here. So your diode's got to be able to block peak to peak voltage coming out of your secondary, your transformer, for a full wave rectifier. Half wave rectifiers, it's only got to be able to block V peak. Full wave rectifier, it's got to drop peak to peak, because when one side is negative, the other side is looking at the positive alternation. So remember that. So if I came over here and said this is V peak is equal to 120 volts divided by 0.707. What you got to do is you got to say V peak to peak. Now you got two answers. You can take V peak, so V peak to peak could be equal to V peak times 2, right? Or you could say this, right? Understand that? Or you could go ahead and double this up to 240 volts, right? And then divide it by 0.707, whichever way you want to do that. So this is the PIV, the peak inverse voltage. This is how much voltage the diode can block when it's reverse biasing before it breaks over. So if you exceed this breakover voltage, that's like a 2x4. If you lay it on the table and you start putting weights on the outside of it, it's going to break over sooner or later. And when that 2x4 breaks, because you've exceeded the weight that it can hold horizontally, then what's going to happen is it's going to no good anymore. So that's the same thing, that's going on with your diode. They called it breakover, reverse breakover for a reason. If you break over a diode in the reverse direction and you don't really protect it with a resistor, which these guys are not protected by hardly anything, then odds are it's going to damage the diode. And the problem we have, normally a diode can go bad solid state devices can go bad in 3 different ways. They can open, they can short, or they can become very leaky, which means they conduct a pretty good deal of current in the reverse direction, which is not good. So let's see, what are we doing here? These are just fractions. Note the answer will be slightly larger than the actual value because VF of the diode is ignored. So this is what the textbook, I think, teaches, is this number right here. So I don't like using fractions and just throwing them out there. So they took 2 V peak. V peak would be equal to 2 times over 7, and then they came up with this fraction. So technically, you can take your VRMS and you can multiply it by 0.9, and that will give you a really good idea of what your output voltage would do, which is pretty neat. So I think this is in the formula sheet too. But your answer will be slightly higher than what you're actually going to come up with because this ignores the drop of the diode. So yeah, this is pretty cool. So volts DC is equal to approximately VRMS. So let's see how that works out. So we had 6.3 volts. And then we take 6.3 volts and multiply that by 0.9 in volts DC. And what do y'all come up and get? So a while ago we got 5.4. What do we get here? So 90%. So 0.567.
5.6.
Yeah, so ain't that neat? So a while ago when we took out the diode drop and went through the math, we came up with 5.4 volts, ignoring the diode drop and just taking the input voltage and multiply it by 0.9. You'll come up close enough. So odds are you could answer just about any question on the test. Unless we had 5.4 and 5.6 on the tests, then 5.6 would be wrong. So this is a really neat formula, but it's now, instead of remembering this V peak over pi and 2 V peak over pi, you're back to trying to memorize numbers, right? This 0.9, which is pretty neat, guys. So any questions on that? So this is solving for all that. By the way, 1.414 is the reciprocal of 0.707. So,
Mr. Raymond,
yes, ma'am.
are you saying that it's okay to use just the 0.9?
Yes, it's fine.
Going through the whole?
Yes.
Okay.
But that's a fraction you have to use. I mean, so that's a fraction you have to remember. and the 1.414. So we're using, we say V peak is equal to 0.707. Well, if you took the reciprocal, if we take the reciprocal, we come up with the opposite. So if you take the reciprocal of 0.707, you come up and get 1.414, which is what, that's coming up right here. And then we're saying 2V peak over pi, and then we're taking 1.414 and multiply it by 2, and then pi, and then we come up with 0.9. And to me, that's really neat. So what we did is we did the whole equation and then solve for the fraction instead of going through the whole equation. So yeah, Janice, 0.9 is going to give you a close enough answer. Remember, it's going to be a little high because we ignored the diode drop, but it's going to be close enough for you to pick out the right answer. So this is neat, and that's back when they came up with a 0.63s way back here. That's what they did. They just went ahead and did all the math, and then they come up with these fractions back here. 0.45. This is half wave, so they did exactly the same thing. So if you use 0.9 for full wave, I skipped over this side, I guess. Then you can use one half of that, a 0.45, for half wave. But that's two fractions you're going to have to memorize. And you don't have to memorize it. In the field you would. Is this on the formula sheet? I don't guess I should. Yeah, so these are on the formula sheet. So, but remember, your answer is going to be slightly higher than what we will probably measure because we're just ignoring the diode drop. And on the next one, we'll come up here. So somehow I went right past this guy, but that's two neat things. That gives you a real fast way of coming up with an approximate answer. And in fact, our other answers are approximation. And what you'll probably see is that most of our answers are going to be slightly higher anyway because we're using a 12.6 transformer, and I don't know what the current rating is on it. Odds are we're not operating the transformer at near its current rating, so odds are that means the output voltage is going to be slightly higher, slightly lower anyway. Yeah. So sorry I skipped over that, guys. So yeah, Janice, it's fine if you want to use those two. And like you said, that saves you a lot of math. And of course, the more math you do, the more chance you have of getting an error in there. So this is 2-to-1. I know this is a step-up transformer because if I look at the ratio, that means it's going to be out, which should be 2 over 1. So that's the way we look at this. Just look at the out over in. So that means if I put 25 volts peak to peak here, then I'm going to get 50 volts peak to peak. I mean RMS here. No, that's peak to peak. I'm going to get 50 volts peak to peak right there, which means, once again, this right here is going to be back to 25 volts peak. So my output voltage, so let's take that. So this is RMS, and since it's a center tap transformer, we're only using one half of it. So the biggest problem I have in this class is people want to use that 50 volts right there. And not seeing the center tap and understanding that we only get one half. So let's try that. So this would be 25 volts. This would be 25 volts peak, right? No, RMS. Ooh. So our formula won't work because the formula depends on it being RMS. So here the output voltage would be, so what would V peak out be? Was it 24 point, no, 0.7. Somebody subtract 0.7 from 25 for me. Oh, here it is right here. Nope. 24.8. No, that would 23.8. There we go. 24.5. No, that's still not right. God, my brain went dead. So what's 25 minus 0.7? No. 20 what?
24.3.
3, yeah. Sorry. Thank you. And then this is V peak out, and then we'd use V peak over pi, right? So this, you got to be careful on this too. So notice what they're giving here. They're not giving us RMS. They're giving us what? They're giving us volt peak, which would be 50 volts peak to peak. That's one of the times when my brain went dead. So y'all see that a few times. By the way, the output current is going to be this. Just once we are in DC, then of course your I, the load, would be equal volts DC over here. It would be 10K. So that's the same thing. Oh yeah, this talks about the PIV rating, or the VRMM, repetitive reverse maximum. This is what they call it in the data sheets that we have. This is what the textbook teaches, and what's so strange is most textbooks teach PIV, peak inverse voltage, and when you start looking for PIV in the data sheets, you can't find it, but it should be obvious from the data sheet. It's going to say the maximum reverse voltage. Most data sheets explain that out. So on a full wave rectifier, it's got to block peak to peak voltage when it's reverse biased, and of course when it's forward biased, it's going to drop whatever type of diode it is. And all these diodes, by the way, are silicon. By far, the most popular diodes out there are silicon diodes. Silicon has a better temperature characteristics than germanium, so they don't, when you reverse bias them, they don't leak as much as a germanium diode does. So this is why silicon has been around for a long time, and silicon is readily available. You know, sand is basically silicon. So silicon is readily available, and plus it's got better temperature characteristics than germanium. Germanium was the first one they used, and there are some still germaniums when they get into, they take advantage of that very low VF. That very low VF of around 3/10 of a volt or 300 millivolts. So they're still out there, but the silicon is by far the most widely used semiconductor making these solid state devices. Okay, we looked at this. Let's see. Negative. So here what we're doing, same features. So what we would do is we're going to look at the diodes, and if the cathode points toward the source, this is going to be a negative power DC power supply. And if the anodes point toward the source, it's going to be a positive DC power supply. This applies to half wave and full wave center tap regulators. So all the math is exactly the same. So if I had VRMS over here, if I had 12.6 volts RMS right there, RMS, then you can take that and multiply it by 0.9, and that would give you the output voltage. But you're going to have to make sure you put negative, and this is another problem we have on test, is they don't put the sign. And if you don't put the negative sign, then your answer is assumed to be positive. So y'all watch out for that too, because negative power supplies are not as popular as positive power supplies. But if we're going to deal with anything, if we're going to generate AC from DC, if we're going to generate AC from DC, then we're going to have a negative DC power supply. So, and we can control that electronically, and we'll actually try to show y'all some output arrangements of stereos and stuff like that. So this would be a negative power supply, what we get out of our oscilloscope. The last full wave rectifier we're going to talk about is called a full wave bridge rectifier. The full wave bridge rectifier uses 4 diodes. During the positive alternation, 2 diodes are forward biased and 2 are reversed. So 2 will always be on, 2 of them will be off. And during the negative half cycle, the 2 that was on for the positive half cycle will turn off, and the 2 that was on, then the other 2 that was off during the positive cycle will turn on, if I said that right. This guy deals with 4 diodes. So this is the layout. This comes from a drawing that we've been using for years on DC, on resistor networks. So I don't know if y'all got into bridges, and I've been talking to the people in DC and talking about the importance of these guys right here. So these are resistors, by the way, even though they look like inductors. And this arrangement became known as a bridge. So now everything that we do that takes that shape, we call that a bridge rectifier. Or we call it a bridge circuit. Excuse me. So this is a full wave, unregulated, unfiltered bridge rectifier circuit. Now, what we're looking at is here we can't look at what's pointing back toward the source, because here's the source. First of all, one advantage of a bridge rectifier is it does not require a center tap transformer. So it does not require a center tap transformer. By the way, normally when they wire transformers, they wrap the windings on top of each other. So what happens is we come over here, and when this guy comes out, when the magnetic field comes out this direction on this one, it's coming out of this one and goes into that one. So that means when this is positive and negative, then over here this transformer would be negative and positive. So what they're doing here is they're putting these polarizing dots up here to indicate when this is positive, when this is negative, this is negative. Now on a rectifier circuit, that means nothing. Just because my secondary voltage is 180 degrees out of phase with my input voltage, it makes no difference. So one thing, they're totally isolated from each other. And another thing, we're using diodes to steer it in one direction. So it works out no matter whether it's going, up or down or up. But all those are polarizing dots, so they can show it like this, and don't confuse y'all. Some transformers, they're wound in the same direction. So if I've got an E transformer where I've got two coming down, and then they wind the windings around this, and they're wound in the same direction. But the only time I know where this comes into play is on pulse transformers. When you pulse, I'll see if I can find one. When you turn on a SCR, the polarity is extremely efficient. So what they do is they put the little polarizing dots on there for you. It's actually on the outside of the transformer. Regular transformers, we don't care. Like I said, because when we rectify it to DC, it don't make any difference the relationship between your primary and your secondary. We're looking for number one. We're looking at the polarities on the secondary. We're not worried about the primary, and then our diodes are used to steer it around. So that's what those dots are up there, by the way. And that's why instead of they can put plus and minus. Normally, what I do is I ignore the primary and I just come over here and put it on the secondary. By the way, this is not in your book. This came out of a Prentice Hall book. So, is this Prentice Hall? No, this is ATP. So what happens, and I'm going to show you a lot easier way to draw this, is I can't use the polarity. So when I take this positive, so right now they're showing this as being positive, and I come over here to my diodes. One of them has the cathode pointing toward the source, and one of them has the anode pointing toward the source. And then when I come down here on the other side of the transformer at the same time, we see your AC always sees a cathode and an anode. So what we're going to look at on a full wave center tap is we're going to look at these two diodes right here. So the cathodes are pointing toward the load. So that means the current flow has got to be in this direction right here, which makes this positive and makes this negative. So on a full wave bridge, if your cathodes are pointing toward the loads, it's a positive power supply. If your anodes are pointing toward the load, it's a negative power supply, which does get confusing. But over here, this is the way it converts, right? So this might be positive in respect to that, but this over here is more positive in respect to that. And this is why I teach when we forward bias a diode, I don't say the cathode has to be negative. If you ever see that on a test, to forward bias a diode, the cathode has to be negative and the anode has to be positive. That's false. Normally, your anode is 0.7 of a volt more positive than your cathode, or your anode is 0.7 of a volt less negative than your cathode. So it's not negative in cathode, and some books kind of teach that, or they don't iterate that, and it's very, very important, because that's going to be, and there's going to be, this is going to be on a test. I'm going to come over here and I'm going to say, okay, I'm going to come over here and I measure 15 volts on the anode. What should the cathode measure to forward bias this? Plus 15 volts. What should I measure on the cathode relative to my circuit common? What should I measure on the cathode if it's forward biased? Silicon. Forward bias. It should measure right around plus 14.3 volts. It's got to be 0.7 of a volt less positive. And this gets people confused. And some people teach it. The anode's got to be negative and the cathode's got to be, the anode's got to be positive, the cathode's got to be negative. And that's not true. And this is especially true if I was to come over on this circuit right here, put my resistor right here, come over here and put my DC source. And my DC source is plus 15 volts. And I make my measurements relative to circuit common. So here's my meter right here. I'm going to put it right there, and I'd measure just about 14.3 volts plus, and when I move it right there, I would measure plus 15 volts. So odds are there's going to be something between the negative and the positive on that diode to protect it. Because if I measured a negative on the cathode and a positive on the anode, that means the diode is probably about a 99% chance that it's open. So you should never measure that. Now, if I come over and put it like this, and put my DC source here, and I measure relative to common, then this right here is going to be 0 volts. It's not going to be negative, and up here this will be whatever. If this is 15 volts, this should measure. It'll measure 0.7, approximately 0.7. So, but the cathode is not negative. The cathode is 0 in relative to common. So you should never measure negative on the cathode and a positive voltage on the anode. It's either they're both going to be positive, or they're both going to be negative, or one of them's going to be zero, depending on where we put the diode in the circuit. So let's follow this thing. Let's follow it. I think they've got it done for us, but we'll go back and we'll trace it too. And once we do this, we'll take a little break, guys. So when the top of my transformer is positive, let's do this in blue, positive, negative, that's going to come over here and put a positive right here, right? It's going to put a positive right there. The positive is on the cathode. This guy right here is going to turn off. The positive's on the anode. This guy right here is going to turn on. When I trace this guy, here comes my negative. I got a negative on the cathode. This guy right here is going to turn on. I got a negative on the anode. This guy here is going to turn off. It's going to allow my current to flow. Current's going to come out of the negative on the transformer. Current flows negative to positive. It's going to go this way. Can't go that way because it's off. It's going to come over here, go down to our circuit common or circuit ground. That represents a wire. This happens every once in a while. Well, I thought that wire was inside the trainer. It's not. You have to run that wire, guys. But what we do when we use a symbol to represent our common, that's going to be one less wire that I have to draw in a circuit, which means now, but what you have to understand, this represents a wire. This represents a conductor. Then it's going to come here, here. It's going to come up through here, right? To common, up through here. Can't go that way. That's off. It's going to go back this way. And it's looking for the positive, by the way. And it's going to go over here and go back in that direction. So negative came up to here. So if the negative's on this side, that means that's the positive side of that resistor. We would get a pulse out of it. So during the next alternation, it's going to switch, which will be the bottom one. So this goes negative, this goes positive. Let's follow the negative over. Negative is going to set here. It's going to turn this guy here on. Negative setting on the anode. This guy right here is going to turn off. We follow the positive around. It's going to put a positive here, a positive here. We got a positive on the cathode. This guy's going to turn off. We got a positive on the anode. This guy right here is going to turn on. We follow our current flow from negative to positive. Going to go this way, come over here, right? Going to go this direction, go back to the common again, come up through this, so that makes the bottom negative. Going to come over here, going to go back this. It's looking for its positive. Going to go this way and go back to the positive side of the transformer. So what advantage does first of all, your VF now, your VF is going to be equal to approximately 1.4 volts. So this is going to become more critical because every time, every current path takes us through 2 VFs. So this means the 90% will be off a little more. We get this out now, and then of course now it's going to switch, so we're going to come up here and get this. So this right here would be equal to approximately 1.4 volts less than V peak. So the 90% would be close, but would still be close, but it's going to be off more than for the full wave center tap. So full wave center tap, we only go through one diode at a time. A full wave bridge, we go through 2 diodes every time. Now there's another way to draw this. Gets kind of complicated. The way I like to draw it is like this, and it's the exact same circuit. is I'll come over here and put 2 wires, right? And then I'll come over here and put, if I want a positive supply, I'm going to point the cathodes up. Then I'll come down here and just draw the other 2. I'm going to bring my AC in and put it right here. And I'm going to jump over this like this just to make sure. And I'd put it right there. And this will be exactly the same circuit. So this one's a lot faster to draw than trying to do the diamond shape. But it's the exact same circuit. Another thing is we can't, when we hook up our scopes, that little old black lead on our oscilloscope is connected to earth ground. If this is connected to earth ground, then that means I cannot put my oscilloscope lead right there. I created a short circuit. So we can't actually, it's hard to look at the secondary voltage of a full wave center tap with a oscilloscope, because of the ground is, the common is not on the transformer anymore. The common is on the load and the diodes. So what advantage does this guy here have? Well, the diodes are a lot cheaper than a center tap transformer. So a full wave bridge is cheaper to build than a full wave center tap. But you'll run into both of them. And we got some battery chargers, by the way, that were used to charge golf carts, and they use center tap transformer. So they use a full wave center tap. So it uses 2 big diodes, and then they have the 2 diodes. So this is where one of the diodes actually went out. It wasn't my battery charger; it was on that golf cart charger. And one of the diodes went out, and it was actually spot welded to the chassis. So I had to grind it off and make a hole and put another mount diode in there. So guys, this is our so let's see if we got some circuit. Bridge output, the 2 diodes in our bridge are always forward biased and in series with the load during the positive or the negative half cycle. If we ignore the barrier potential of the 2 diodes, the peak output is equal to peak secondary voltage, if we ignore them. When D1 and D2 are forward biased, D3 and D4 are reverse biased, and they're going back to this thing right here where they're giving them numbers. By the way, this is a standard designator for diodes in a circuit. So if you look at a schematic, D is used for diodes, T's are used for transformers, L is used for inductors, C is used for capacitors, U is used for integrated circuits, either that or IC. They like to abbreviate these schematic symbols with one letter, and then they'll put a number out beside it. So like D1, D2, D3, D4. I'll try to find. In fact, we'll probably break the trainer apart and look at the schematic. And when they designate that and then they paint that on the circuit card, it makes it easier to find these parts, because a schematic is going to show you the smallest way possible in the logical operation of the circuit. But when an engineer is trying to put these components on a printed circuit board, they're concerned with crossing wires. So a printed circuit board, you can't cross their conductors are basically uninsulated, so you can't cross them. So they're concerned with how do we get this conductor from point A to point B without crossing other conductors. So the components on a printed circuit board are not going to be laid out like the components on like the schematic. So to help you do that, they're going to put these part number, those designators on there. If they don't do that, then you get very upset. But just about all I'm doing, I was looking for a printed circuit board. So R, I forgot R. R is resistors. There's my camera. Oops, it didn't go to it. Oh. I'll get to it in a minute. Here's my camera. There it is. So this is a circuit card. I'll see if we can zoom in on it, and I'll pass this around in the class. But hopefully you can see they're calling this CR1, which is not a Norman designator, but R's. Then the transformers are they're calling they're calling these Q's, so these must not be there. These are integrated circuits. U. So normally what they try to do, and what they would do, even though this guy here doesn't use some of the standard designators, the schematic would use these designators, which makes it easy to find the parts. And you can see they're ultimate gold, and you can actually see these. We call them traces, by the way. Those are the actual conductors. And the layout, it's really amazing how they can do this, where none of these conductors cross each other. This one is not as hard because this is what we call this actually has conductors on both sides. Some of your printed circuit boards only have conductors on one side, the bottom side of the board, and then of course all the components solder into that. So this is a typical, very small printed circuit board with all these devices, and of course we would look at this in a schematic. So guys, let's go ahead and take a 10-minute break, and then we'll come back and look a little bit at this. We'll see if we can basically look at a circuit, and we'll figure out what we need to do about the worksheet and how we're going to turn that in when we get back off break. So let's go ahead and take a 10-minute break, and we'll start my stopwatch.
Hey, Mr. Ryan, let me ask a quick question.
Yes, ma'am.
How long will you be up at the school?
I'll be at the school into pretty close to 5 o'clock, but I'm in class the whole time. So as soon as I get out of this one, I have a 30-minute break between my classes, and my other class goes to 4:15. So if you can come by a little after 4:15, that'll be great. Or is that? Yeah.
I have a class that starts at 4 o'clock.
So Tuesdays and Thursdays, I need to pause the recording. Then if one of the diodes open, then we end up with a halfway rectifier, which means our output DC voltage would be 1/2 of what we anticipate. If one of your diodes shorted, then you're going to have a short circuit, because what would happen, and it should, hopefully it'll blow a fuse. So what I would do is I would come over here and I would replace this with a straight piece of wire. So this diode's going to be on all the time. So when this goes positive, this guy right here turns on. Here it comes through here, this cycle, that's a straight piece of wire, bomb, and it comes back here and we have a short circuit. So in a full wave bridge, center tapped, if one of your diodes short with a short circuit, and hopefully it will blow this fuse right here. Okay, we try to fuse the primary. If we use one fuse, we try to fuse the primary because it protects both sides of the transformer. But what people don't understand is if this is a 1 amp load, they think they got to put a 1 amp fuse over here, and that's not true, because the current, if it's a step down transformer, so if it's a 2-to-1, then if you put 1 amp over here, then your current over here is going to be 1/2 of that, so it'll be 500 milliamps. So this confuses some people. They got a 5 amp supply, and they're fusing it, with a 1 amp fuse in the primary. Now, roughly, I'll try to give you all the actual NEC ratings on transformers. Normally, we understand that in power supplies, we have a lot of surges and everything when you first turn power on. So the power supply has to let these surges go through. So it's usually at least 150% bigger over there. But like I said, there's a rating. I'll give y'all, I don't know if I put it on this side or not, where you can actually, depending on the current load of the transformer, what size fuse you should put over there in the primary, and it's going to be a certain percentage. If it was a step up transformer, then the fuse in the primary would actually be bigger than the fuse required by the load. So if we get an open in a full wave rectifier, what's going to happen is it's going to convert it into half wave. So that means if I'm not filtering it, it means my output voltage will drop down to 1/2 of what I expect. And that's troubleshooting power supplies, guys, is not putting meters in there to see what's there, putting your meter there to verify what you expect. So this is a circuit I have hooked up. Don't pay any attention to this. And let me switch over to my camera. And like we said, the connected circuit and the oh my goodness, let me just click on it. I'm trying to hit tab to go through my slides, but it's going through all those errors. So here's my circuit. So center tap, we're using the Hogue transformer. So this is my 12.6 volt center tap transformer. Okay. And then of course we're coming in on both sides. The diodes are not in parallel. Now notice I have the cathodes connected together, if you can see that. So here's a cathode, and here's the load. They're all connected together. But over here, I'm going to come down a little closer if my camera will focus. Yeah, it's doing a real good job today. Here, this anode is lined up in a line, and then this anode is lined up in a line. So their anodes are not connected together. Cathodes are. Here's my common. So the common's going to the center tap of the transformer. Okay. I made it black, and then my two outside leads are red. So here's a circuit, real simple to hook up. Biggest problem we have here is people see the diodes in parallel, so they connect the anodes together. This is a positive power supply because the anodes are pointing toward the source. So we should accept our pulses to be positive. So this is the oscilloscope. I'm going to lower it down a little bit. And so there's my oscilloscope. And it's picking up the edge of the trainer. So here's my oscilloscope. And what we have, this is the speed. So the slower we put it down, the harder it is for it to read it. Okay, and our timing, our calculations would be off. I mean, we would have a bigger error because we're putting more information inside a single thing. It's like the analogy I use. It's like the speedometer on a car. So you got a speedometer on the car, and you put it right here, and right over here is 120 miles an hour, and right beside it is 0. And you're trying to figure out how fast you're going somewhere in there. Well, the units would be so small that it would be almost impossible to discern. So what we do is we spread that out, and we'll put 0 over here, and then 120 will be way over here. And then we have all these different miles per hour. Okay. And so if we spread it out, then we can come in here and we can see these units, and we won't get as many tickets. So what we do on oscilloscope to spread it out is, if I can come over and get my oscilloscope here. What we do on the oscilloscope to spread it out is we make the scope go faster. So this is here, if y'all can see the rating on it. So right now I have it on 5 milliseconds per division, which means each minor division would be worth 1 millisecond and would be hard to read. So what I would do is I'm going to come over here and decrease my time per division, and now it spreads out, and now we could actually measure the time for this pretty easy. Then we'll take the position. So this is horizontal position, which y'all can't see, and I can actually change the position. So now I got it 1 millisecond per division. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, and about 1 division over. We're expecting about 8.3 milliseconds. So now I know this is 60 hertz for 1 cycle. So 8.33 milliseconds. If we took the reciprocal of that, we would find out that it would come up and give me 120 for a cycle. So this is 120 hertz cycles per second, because now we're turning in both sides. So this is what it looks like on an oscilloscope. So my RMS voltage is 12.6 volts, and this is a full wave center tap. This is my circuit. You can see it's operating correctly. I'm gonna drop out of my PowerPoints, and I want y'all to, when you calculate my output voltage I should measure, I want you to put it in the chat window. So just put it in the chat. Once you calculate what you think this voltage should measure when I measure it with my DC voltmeter. 12 volts RMS on the secondary. Full wave bridge. Now that's 12.6 volts across the transformer. It is a full wave center tapped.
Mr. Raymond,
Excuse me?
Are you showing us something?
I'm showing you the split screen. I gave you I gave you the input voltage. It's a full wave center tap. The RMS.
I'm just saying your mirror.
It's what? I know this is where I have to go to see your answers. So I'm back to the mirrored screen. We looked at the circuit, so y'all don't need the circuit anymore. It's a full wave. I'm using a 12.6 volt center tap transformer. It is a full wave center tap, unregulated, unfiltered, full wave center tap circuit. What he does is they use the entire secondary of the transformer, and that's the way, unfortunately, that's the way it's rated. And we're only using 1/2 of it at a time. So I could say my volts DC would be equal to approximately 6.3 times 0.9. That's the easiest way to do it. And what do we come up and get? So as soon as you got 11 volts, I knew exactly what you did. And like I said, guys, that is on a center tap transformer, that is the most problems we have, is when they give the rating of the transformer as a 12.6 volt center tap transformer, then you're going to try to use 12.6 volts. But it's center tap, which means we're only using 1/2 of it at a time. So instead of using the 12 volts to calculate this thing, the 12.6, we're going to be using 6.3, which is what we should expect. And what's this? Anybody got it yet? About 90% of that. Which is good. Or we could do the whole math. I could say my volts DC would be equal to 2 V peak over pi. V peak out. So I'd say 6.3 divided by 0.707. This is V peak on the secondary. So 6.3 divided by 0.707 equals that, minus 0.7 equals that, divided by pi equals that. So we should expect around 2.6 volts when we measure this with a DC voltmeter. We could come up here and do the other formula and see how close it comes up to give us. Clear 6.3, clear 6.3 times 0.9 So I did something wrong. So it should be about 5.7 volts, which I should have expected 5.7 because that would be about 1/2. So let's see what I did before. So it's going to be 6.3. Crap. 6.3.
I had 5.7 when you multiply it by the 0.9, but when you do the other math on it, it comes up completely different.
6.3 divided by 0.707 comes up and gives me that, right? Minus 0.7 gives me that, divided by 3.14. And you're right. So let's measure it and see if the 95% works. So let me find my camera again. And let me put my meter up here. So what I'm going to do is I'm going to raise it up because we don't need this oscilloscope. And then we'll figure out what we're doing wrong. And it's always good.
I believe on the first one where you stretched it out on a long math, you did a half wave. We didn't have the 2 times speed.
That's exactly right.
Divided by pi.
Thank you.
So if you come up with just what you had and multiply by 2, it comes up with a 567.
There you go. Thank you. I knew I was doing something wrong. So we're going to come up here. We're going to look across our load. Let me find my best laid plans. I'm missing my positive lead on my there it is, on my meter. So I got it on common, got it on volts. Thank you, Lee. And then I'm gonna measure across this. Can y'all see my meter? I'm gonna measure across. We should say about 5 point. And it's measuring 4.8 or 4.9 volts. So why is our measurement? Why is our measurement not 5.7?
Because what your diode drops, that's 7/10.
Well, no, we calculated a while ago with the 7/10. I just didn't multiply it by 2. That would still came up and gave me what? That would still came up and gave me about over 5 volts. So you're right. That could be this, but odds are this is not exactly 12.6 volts. So if we measure the AC voltage on our transformer, it's probably going to actually be less than 12.6 volts. So 2. Yeah. So one way we got 5 point. What was the first one we got? 5.6. The other way we got 5.2. So it is closer, and this is what I'm saying. The 0.9 is good, but it's always going to be a lot higher than what we're going to measure. But it's close enough to see if it's working or not working. So here's my transformer right here. I got it on AC, and I'm going to measure it. Oh, got it on AC. I'm going to come up here and measure it. So this is my input. So see, it's only measuring 12 volts. So it's missing 600 millivolts. So since it's missing 600 millivolts, then that means that's going to cause hers to be lower. But what we're doing and what I'm trying to iterate, even though I forgot to multiply by 2 a while ago, even though what I'm trying to iterate is your math is going to be perfect, but your components are not. So what we're doing is we're doing a close approximations to what we expect to see. So if I got over here and did measure 2 volts, so let's come up here and open up one of my diodes. So this is open up my diodes. And I'm expecting 5.6 volts out, and I come up here and measure across it now. Let me put it back on DC. I come up here and measure across it now. Then we notice now there's your 2 point something volts. So right off the bat, I know it's measuring 1/2 of what it's what I'm anticipating, which means I know something's wrong. And of course here, since we talked about it, I know one of my diodes is open. So, but if we come up here and open, so the only way you're going to get an open circuit here, and if I come over here and short one of the diodes out, that would be dangerous because that would create a short circuit. So I'm not going to do that because that would blow the fuse in the trainer. But what I was talking about is full wave bridges. This gives people problem because we specify the transformer as what the outside is, right? The transformer. So that transformer up there on your telephone pole is rated at 240 volts AC. It's a full 240 volt center tap transformer. Well, the problem is your outlets, which is what you're using, you're seeing 120 volts because you're only using one half of that transformer up there, and that's a common mistake. That's a very common mistake, and I told you that is y'all use what y'all used the whole transformer and y'all came up with 11 volts when it was actually one half of that. So the 0.9 worked out really well. It's just that you're going to have to remember what you measure is going to be. It could be what maybe could be a volt difference. So, but it's close enough to determine if it's right, if it's working or not working. So let's see. I think I got some more diodes up here. I do, and when you set up the full wave bridge, it's actually easier if you wire it like this. So what I've got is I'm gonna bring my AC in. So I'm gonna wire, when I wire the full wave bridge, I'm gonna wire it like this. We're gonna make a positive supply, and this gets people confused.